All right. So now I describe the electrons in these states by these wave functions psi. But there is another language, as I alluded to last time, another language that is used to describe the wave functions. And that language is this orbital language. Right? So we talked last time how an orbital is nothing other than a wave function. Right? It is the solution to the Schrodinger equation for the hydrogen atom. It is actually the spatial part of the wave function, meaning there's another part of the wave function called the spin part, but we'll look at that a little bit later. All right? Okay, and how are we going to label these wave functions in the orbital language? Well, we're going to label them by the principal quantum number n, and of course, the angular momentum quantum number L, and then the subscript here, m, for the magnetic quantum number. But what we do is, instead of using the actual value of L, we have a code, we got a letter code. So, for example, if L is equal to 0, we call that the s orbital. So in the case of the 1, 0, 0 state, if you have an electron in that state, the wave function that describes that electron is the 1s orbital, or the psi 1, 0, 0 wave function. All right, this is the principal quantum number. This is the code S for L is equal to 0. And then likewise, in the 2, 0, 0 state, the wave function that describes that electron will be 2s, because here's the n equal 2, and then our code for L equals 0 is s. Now, when L is equal to 1, again, we don't use L equal 1, we use a letter. That letter is p. We call that a p orbital. So this state here, the 2, 1, 1 state, is going to be a 2p wave function, or the electron in it is going to be represented by this 2p wave function. Same thing for this. Same thing for this state. They're all 2p's, okay? Because L is equal to 1 for all these three states, and n is equal to 2. Now, if I had here an angular momentum quantum number of 2, we'd call that a d orbital. If I had one that L is equal to 3, I'd call that an f orbital, and so on and so forth.